So this is the last demonstration that I promised you, and this is basically where we're talking about the momentum transferred, how to transfer momentum to water. Water basically actually carries momentum, and so one of the last questions in the lecture was, well, what happens if you hit a glass bottle with a hammer? You don't want to do this at home, really. You know, it's kind of fun, but you need basically a rubber hammer, and you really should have some work gloves. I haven't shattered a glass yet, but I wouldn't really want to, and hopefully this won't happen. Now let's just show what happens with the first one. The idea is that you hit it. You can actually kind of hear it. Hear it ting. And you can see that basically it breaks pretty cleanly, actually. Only one side basically broke off. And so the question that one can ask yourself is, well, why does it do that? And let me get my writing pen. And the idea is that when you have this glass bottle, it's got a lid, and the glass bottle's down here. When you hit it with the hammer, like this, so you're basically forcing the hammer down onto the glass bottle. What you're doing is that you're essentially transferring momentum to the glass bottle itself. And so the point is that the glass bottle clearly moves down in reaction to the impulse provided by the hammer. But the problem is that the water, in this case, this iced tea, which is sitting here, the only interactions it has with the bottle basically are these sort of viscous interactions with the wall. And so effectively the glass bottle moves down, and the inertia of the water essentially keeps it in place. Now up here you've got air, and so what happens is that this compresses basically as the bottle moves down. And so then sometime later, essentially what you have is, because this now builds up a significant pressure, is that this suddenly reacts because the pressure can exert a force on a liquid, is that eventually the pressure drives the fluid downwards. But now the problem is that you got the fluid moving, but there's nothing really to stop it from moving except for the bottom. And so once again, in order to stop it moving, because eventually it has to come to rest, is that the pressure at the bottom of the fluid basically has to skyrocket. And so what that means, though, is that there has to be an equal and opposite pressure on the glass. And so there's a force on the glass bottom, which is equal to the pressure times the cross-sectional area. And since the cross-sectional area is so big down here, you can actually get a significant force. And so what happens is, rather than the bottom actually sort of exploding outwards, it pretty much shears off the bottom of the glass. So just let's look at that again. Again, here's another bottle. And again, you want to be careful about how you hit it. You can hear it ting, and that essentially is the tinging is the air essentially getting compressed. And so as you whack it, eventually it just breaks off. And this time it actually sheared almost beautifully off. And you can see just a clean break all the way down. Root beer bottles work really well, in fact. But these iced tea bottles, hard to find glass bottles anymore, but these work pretty well. So that's the last thing that we're going to talk about this quarter. And so the idea is that water carries momentum, and so trying to basically get rid of that momentum involves an impulse, which involves a pressure. And so this is why when you close the valve really quickly on a valve, in an old house, you can hear the pipes as a whole just basically shudder in response, because essentially it's the pressure causes interactions with the pipes as well, and that's what causes water hammer. So anyway, it's been a pleasure. I hope everything goes well with the final exam, and I look forward to seeing all your term papers shortly. Have a good break.